We're going to start a new topic. It's reflection, refraction, and optics. All right, that's our new unit. We're going to rock it through this really quickly. Okay, now we're going to talk about this mostly in terms of light. Okay, because it's what we see. However, these same properties can apply to any wave. All right, sound waves, water waves, microwaves, whatever, okay? So when we get into lenses and mirrors, mirrors work for sound waves and water waves as well. The mirror just won't look like a mirror that we're used to seeing, okay? When we get into lenses, there are lenses for microwaves and different things like that. It's just that the lens will look different because it operates for microwaves. So when we talk about these things, they actually apply to all sorts of waves. It's just that we're kind of gear them towards optics because that's how we use them, how you will use them in your everyday life. But there are microwave lenses, there are water wave reflectors or sound wave reflectors. We'll talk about that when we get there. All right? So we're going to. So light will be what we normally or mostly talk about in this unit, but it applies to all waves. All right? Okay. Just as a background for light, don't forget, light is made up of waves. Okay, it is a wave. Actually, it is a wave/particle, which we will talk about when we get into modern physics in another week. Okay? Which will be our last unit. This is our second to last unit. Light. What's light?
Light is just the visible.
Yeah, oh, visible.
Electromagnetic wave.
What else?
The color.
X-ray. Okay, where are we going here?
Alright, so that's all visible. X-rays,
Ultraviolet, gamma rays.
infrared,
Is that light?
ultraviolet, micro.
Radio. Gamma.
Alright, that's our entire spectrum. There is no difference between any of these. They're all the same electromagnetic wave, with the exception that they have a different frequency and wavelength. Okay, as we go up this way, the frequency gets higher. As we go down this way, the wavelength gets longer. But if we take and multiply frequency times wavelength together, they will equal c. It looks like an E. It's c, the speed of light, because velocity equals frequency times wavelength, right? So as the frequency gets higher, the wavelength gets smaller. Okay? These radio waves can be really long, like football field length.
Wow.
Okay? Really. Like for instance, AM wave for AM radio, I think that, if I remember correctly, that's 100 meters, somewhere in that range, if I remember correctly. FM is somewhere around a meter-ish. Okay? And then, well, let's just figure it out quick. Okay, favorite radio station?
96.3.
89.3.
96.3. You're a country fan. All right. 96.3. Is that AM or FM? Okay, so that's megahertz. Okay? So figure out what's the wavelength of that. Everybody, calculators out. Go.
Oh, that's not that.
Hey, by the way, this is a common mistake for students. There'll be a problem like this on the test. It'll say this radio wave is a frequency of this, and students will go, rightfully so, V equals, velocity equals frequency times wavelength. They'll put this in for their frequency. They'll remember to make this times 10 to the 6th. But then they'll put in, because it's radio and they hear it, they'll put in the speed of sound. Okay, it's not the speed of sound. The wave travels at the speed of light, which is c, which is 3e8 meters per second. Okay, so what's my wavelength?
3.12.
What's that?
You know what I watched?
What?
Pirate radio.
I
Love that movie. Oh, it's great.
What is it?
Yeah, love it.
3.12 meters. Okay, so let's say you wanted to listen to the traffic report, and you listen to 1080 KRLD. Okay, KRLD is AM. AM is kilohertz. So 1080 kilohertz. Yeah. All right, so V equals frequency times wavelength. So that's 3E8 meters per second equals 1080 e to the third hertz.
Whoa. So that's 277.
278 meters, so it's the length of a football field. Actually, three football fields almost.
Bigger range.
All right. Now, the deal is that different wavelengths have different frequencies, right? And the different frequencies interact with different size molecules, okay? So like, for instance, these radio waves will pass through you. They are too big to interact with your molecular structure, okay? Microwaves are of the right frequency so that they're about the size of molecules, some of them anyway. And so the one that we're familiar with, the microwave oven, is a particular frequency just to vibrate the molecule of water. But I think I wrote this down before, didn't I? Yeah. It takes the molecule of water and it makes it vibrate. Okay? I think it vibrates this way and back. I don't remember. And it just heats up water, and that's it. Okay, infrared is a frequency that is just the right frequency in that range. A lot of times these are called heat rays because they are the right frequency that they interact with a broad spectrum of molecules, and they make the molecules vibrate. And so they will make, like if you have these hitting you, they'll warm you up because they make all your molecules vibrate. And when they make your molecules vibrate, that is heat, right? Temperature going up in your body. All right, visible is only important because our eyes are sensitive to it. All right? Ultraviolet has enough energy to penetrate through your skin and give you a suntan or a sunburn or cancer eventually if you get too much of it. It'll mutate your gene structure. X-rays have even more energy. These things can ionize stuff. If I hit like materials with X-rays, it can ionize them, knock electrons off. Okay, and that's enough energy that it'll go through your soft tissue, but not your bone. So when you get an X-ray, it gives you essentially a shadow picture of your bones. Okay. X-rays can also give you cancer if you get too many of these. Gamma rays have enough energy to interact with the nucleus of atoms, all right? And they're small enough to be in that range. All right, so these interact with different types of materials depending on the shape and structure of the molecule and atom and what the frequency and wavelengths are, all right? So these are great big, these are shorter, and they get shorter still from there, all right? Remember, visible light is roughly 700 nanometers on this end to 400 nanometers on this end. Okay? And the frequency is somewhere in the times 10 to the 14th hertz range. Okay? Very fast. But about mid-range of the whole spectrum. All right? So remember, we can't see things smaller than that. All right? Because the waves that we use in our eyes are that big. Okay, if you want to see something smaller than that, you have to use a different type of wave. All right, so that's the spectrum. Now, let's move on to our first law in this unit, the law of reflection.
You do something.
So they still cover
I
the
hate
same
these
range?
things. What's that?
So they still cover the same range? AM and FM? Or they cover-
The question was AM and FM, do they cover different ranges? It turns out that the atmosphere has what's called an ionosphere out here. The ionosphere is where, if I remember correctly, where the light's radiation hits the molecules in the upper atmosphere and ionizes some of the molecules, so they're charged. And they happen to be the right size so that AM, that band of AM, can go up and hit the ionosphere and bounce back. Okay? Also, since AM waves are so much bigger, remember the thing that we called diffraction, right? Where a wave bends around an object. So like if you're standing here and a wave comes up towards you, okay? If the wave is a really short wavelength, like light, then what will happen is it'll cast a shadow back here, right? A nice, crisp shadow of you. Ooh, look at that shadow. Right? However, if the waves are bigger, about your size, or even bigger, then the waves have a tendency to bend around the boundary, right? Remember we said that? That's called diffraction. All right, so since radio waves, AM radio waves, are so large, hundreds of meters, they have a tendency to bend around things, and they also tend to bend around to the curvature of the Earth a little bit as well. FM has a shorter wavelength, so it doesn't have this bending property as much, and also it won't bounce off the ionosphere. So what happens is an FM tower is right here. It'll broadcast, and the waves will go like that, and if you're beyond the curvature of the Earth, which is roughly about 100 miles, then you'll lose your FM station. Some of you will notice that when you drive out from the Metroplex, you get a certain distance, and all of a sudden,
Horizon is 100 miles away.
roughly speaking, for a tall tower, about 100 miles, you'll start to lose your station. Now, AM stations, like I can pick up, if I'm really desperate for Cardinal baseball from St. Louis, I can pick up the AM station at night in St. Louis, okay, when there's less interference. Because it'll curve around the Earth and bounce off the ionosphere to me. All right? So, also in, well, anyway, so that those waves will bounce around more for AM. All right? They have like ham radio. If you know what a ham radio operator is, it's a particular band of frequencies that will bounce around off the ionosphere and the Earth, and you can talk with somebody else on the other side of the planet just by picking up your little radio and broadcasting, and it will bounce around until they can hear it, which is pretty cool.
That's cool.
All right.
You don't need to annoy people in China.
All right, so here we go. The law of reflection. Okay, you ready? You ready? Ready? Ready?
I'm ready.
Angle in equals angle out. Done.
I like that.
The law of reflection. Here's how this works. Light ray.
Homework is just like.
Now, here. There are two ways to draw a wave. You can draw the wave front, like the waves coming up like this. Okay? Come on, boys. The wave front coming in like this. And then it hits this boundary. This is the original medium. This is medium number 2. Now remember, all that stuff we talked about waves last unit applies here. When a wave hits a new medium, what happens? It can speed up or slow down depending on what the medium is, right? And when it hits the new medium, if it has a different transmission speed, then will all of it transmit? Then what happens to the other part? It reflects, it bounces off, right? Okay, so here the deal is this wave will come into this new medium and it will change speed, and when it goes to the new medium change speed, some of it reflects. So that's the part we're interested in right now, just the reflected part. The reflected part will bounce off. Well, these waves will bounce off like that. Well, drawing wave fronts is a little challenging to see what's going on. So there's another way to draw this same picture. And the same picture you draw it with what are called rays. Rays are just an arrow, a vector, showing you the direction that the wave is traveling. The wave travels this way, it hits, and then the wave travels out that way. Okay? Now, the only thing funny about the law of reflection is how the angle is measured. The angle is measured from a special line, which is called the normal line. The normal line is a perpendicular, and they don't really use this term anymore in math, I don't guess, because students don't really hear it in math class anymore. But a normal is a perpendicular line to a surface. Do they still use that? Okay, excellent. Because sometimes I ask students, they talk about normal lines in math, they go, oh.
Yeah, we've heard it.
Calculus.
Calculus.
All right, in calculus. All right. Now, this seems kind of silly because we really have two ways to measure our angle. We could measure our angle up here to the normal, or we could measure it down here to the surface. Okay? One of the two. But it turns out that in most cases, geometry-wise, it's easier to draw a normal line than it is to draw a tangent line. Because some of our surfaces will be curved. And if our surface is curved, and the ray comes in and hits at this point, it's actually easier to draw a normal line because a normal line is a radius to the curve. Whereas the tangent line would be harder to draw in most cases. So it's easier for us to measure to the radius, or the normal line, than it is to measure to a tangent line. Okay? So that's why it's picked that way. So that's the only thing funny about it. The angle in equals the angle out. And there's really nothing more they can do with that. That's it. All right? Now, if the surface is smooth, then you get a regular reflection, and all the light rays that come in all bounce out together. But if the surface is irregular, you might get something that looks like this, where the light rays bounce off like that, and it appears that the law of reflection is not working. Okay? In a case like this, if you take this surface and blow it up so you can see it close up, then the surface has irregularities in it, and what happens is the light rays are coming in and bouncing off like that. And in each surface, the law of reflection works. Okay? So, that's the law of reflection. Got it? Excellent. All right. So, this takes care of what happens when a light ray hits, or a wave hits a new surface at an angle. Now, number two, don't forget that when we had a wave coming up and hitting a boundary like this, that we had a reflection. But our reflection could come in one of two different varieties. Our reflection could come back like this, inverted, or our reflection could come back upright. Inverted or upright. Okay? Remember? Our wave coming in could stay on the same side, or it could flip over. All right? Now, since a wave like this, if it's a nice traveling wave, if the wave comes back upright, then it stays in phase. But if the wave comes back inverted, then the wave flips over. Okay? Now think about that for a sine wave. If you got a sine wave, and a sine wave looks like this, if I flipped this wave over, what will it look like? It looks like a negative sine wave. Or you could say that, look what happened. It looks like the wave shifted over, right? This trough here, instead of it being here, it's here instead. So it's been shifted by half a wavelength, or we could say, think of it as a circle. It's shifted 180 degrees, or it's been shifted out of phase. It's been flipped over. Now, for those of you in pre-calc, calculus and all that, so it's been shifted what? Pi. The function has been shifted pi, or we generally say in physics class it's been shifted 180 degrees, or it's been flipped over. So this is a phase shift, and this is no phase shift. And this phase shift is a 180-degree phase shift. It's been inverted. Okay? It's been inverted. Now, our eyes cannot tell the difference between upright and inverted waves. We have no way of distinguishing that. But mathematically, it'll make a difference for some optic phenomena, which we'll talk about in a little bit. Okay? For some optic phenomena. So just keep that in mind. So when will it be inverted, and when will it come back upright? When will it have a phase shift, and when will it not have a phase shift? Yeah, when it hits a more dense material, it'll come back flipped over. When it hits a less dense material, it'll come back upright. So, see if you can guess this one. What if, here's a light ray coming in like this from air to water. Oops. And it bounces off. That bounced off wave, will it be upright or inverted? No phase shift or 180-degree phase shift? No. Yeah, which is more dense?
Water.
Okay. Now, that one's pretty easy to guess because it's physically more dense. Sometimes it'll be harder for us to tell, like glass and plastic. What if it goes from glass to plastic? We may not be able to tell. There will be a way for us to numerically tell whether the wave gets inverted or flipped over or not. Okay, we'll talk about that in just a bit. All right? Okay. Let's now talk about the wave that actually enters the new material. Okay? See that? Okay, here's our incoming ray. Okay, when it hits the new material, draw your normal line. You may need to get out a protractor if necessary. And then it will bounce out where this way angle equals this angle. All right? Piece of cake. Now, when the wave hits the new medium, okay, it's going to either speed up or slow down. Well, actually, it could stay the same speed. If it stays the same speed, what will happen? Actually, if it stays the same speed, then all the wave will just go straight through and you won't get any reflection. Okay? All right, but it might speed up or slow down. Well, let's see what happens. So here we go. Here's our medium difference again, and here's my original wave coming in. Okay? My wave is coming in this way. All right, I'm going to put 1, 2, 3, 4 dots on here. 1, 2. All right. 4 points on the wave. Guys. Okay, and the wave is going this way. It goes this way, this way, this way, this way. This one goes this way, this way, this way. But let's say that the velocity in the old medium and the velocity in the new medium are not the same. Let's say the velocity in the new medium equals 1/2 of the velocity of the old medium. So instead of this point going this distance, it's only going to go half that distance to right here. Okay? One-half the distance. All right, now, the wave progresses to here. This spot continues to go only half the distance. This spot now only goes half the distance. This one goes the original distance and the original distance. Okay? So now, this spot continues to go half the distance. This spot goes half the distance. This spot now goes half the distance. And this spot goes the whole distance. Got it? Anybody see what's happening?
Turning into a web.
If I erase these, it's a little easier to see. What's happened is that this wave out here is traveling this direction. But what happens when it enters the new medium? It's now traveling this direction. It's changed direction. Only because it's changed speed. All right? Now, if we look at this, this was going this direction. All right? Now I'm going to redraw it over here. It was going this direction, but now it's changed to this direction. Instead of going straight, the original path, here's our new path. Okay? So we have a new angle to measure with our normal right there, theta 2. Got it? Now, what I've drawn here is if it goes from fast to slow. Okay? Going from fast to slow, or faster to slower. Okay? If it goes from faster to slower, look what happens. The angle with the normal decreases every time. What if it would go even slower?
It decreases.
It would decrease even more and get even smaller. So the bigger the difference, the bigger the change in direction. Okay, general rule of thumb, everybody. General rule of thumb. Faster speed equals bigger theta. Or some students remember it as
This is the fraction.
bigger speed equals bigger angle. Smaller speed equals smaller angle. This will always hold true except for one case, which I'll tell you in a minute. Okay? All right, so if you slow down, go from a bigger speed to a smaller speed, you're going to have a smaller angle when you enter. Guess what? What if I would redraw this, but my new speed instead would be twice as large? What would happen then?
Your new speed is twice as long as an angle.
If we came in like this, and this velocity 1, velocity 2 is equal to twice velocity 1, so it doubled its speed, what would happen then? Well, this spot right here, instead of going only this distance, would go this distance, right? And so look what happens, is the wave changes direction again. It was going this way, but now it's going to be going this way. So it goes from this to this if it speeds up. So slower here, faster here. Here's my normal. Here's my theta incoming. Here's my theta outgoing. Wherever you're going faster will be the bigger angle. Does that make sense? All right? Here's your one exception. What if my wave is coming this way, straight in? Yeah, because my wave comes like this. If it speeds up or slows down, it's still going to go in this same direction. Does everybody see how the geometry is going to work out on that? If it slows down and goes only this fast, it's still going in the same direction because it hits perpendicular to the surface. Or it comes along the normal with an angle of incidence of 0 degrees. It's kind of a trick question. Okay? The angle of incidence here is 0 because the normal line is right here. So my angle right there is 0. All right? Okay, so riddle me this then. if this is air and this is water, actually we haven't talked about that yet. If we start in a medium where it's going V, and over here it's going to go 3 times V, and I have my original light ray coming in like that. So the original speed over here is V, the new speed is 3V, the light ray was going this way. Which way will it turn? Will it turn down or up? We have several votes for up. There's my incoming angle. It's going to go faster. The only way for it to go, if it's going to go faster, it's going to turn away from the normal, right? It'll have a bigger angle. So there's my theta 2. Very good. So it'll speed up. And it'll turn away from the normal. Wherever it's going faster, the angle is bigger. All right? All right, so how do we know what speed the light goes in a material? Well, you can measure it. You can measure it now that we have high-speed timers and things like that. It's not that hard. But you can measure the speed of light in something. Because velocity equals change in distance over change in time. All right? You send a light ray through it. Know the distance it takes to go through. Know the time. You can find the velocity in that substance. Okay, here we go. They have something called index of refraction. It is a number that lets you know how fast something's going relative to the speed of light in a vacuum. Okay? Index of refraction is n. N equals C over V. Okay? What's C?
Speed of light.
C equals speed of light. What's V? It's the speed of light.
Whoa.
In that medium though, right?
Okay, the trick is this is speed of light in a vacuum, and this is speed of light in the medium. So this is equal to 3E8. All right? And this is the speed of light in the medium. And they take these things and they measure the speed of light, and then they calculate the index of refraction. All right? All righty. Actually, there's a cheaper way to do this than actually measuring it this way, but we'll find out in a minute. All right? Yes, much easier. All right, so you end up with a whole table of these indices of refraction. So N for a vacuum. Oops. What would the index of refraction be for a vacuum? 1, because you'd have speed of light over speed of light, which gives you 1. Speed of light for air. I'm sorry, the index of refraction for air. It's like 1.0003-ish,
Do we need to know the difference?
which we call 1. The only reason we would never call it 1 is if we're comparing a vacuum to air. Then there might be a difference, so we need to do it then. But for us, air, we're going to call 1. Okay, water, H2O, 1.33. Okay? Plastic. There are different types of plastic. So you're talking somewhere around 1.3 to 1.6, somewhere in there. Okay, glass. 1.4 to 1.7-ish, somewhere in there, depending on what kind of glass. Stainless steel glass. There's actually like crown glass and flint glass. There's different varieties, depending on what kind of sand they use to make it. Diamond, 2.42, if I remember correctly. All right? So will you please figure out what's the speed of light? Let's have this group over here figure out the speed of light in water. Let's have this group over here figure out the speed of light in a diamond. You ready? Okay, what'd you get for velocity in water? What'd you get?
2.26
2.26 e to the 8 meters per second. That's still ridiculously fast. What's velocity in diamond? 1.24 e to the 8 meters per second. Okay, still ridiculously fast. Okay? And in your normal life, diamond will be the one that has the highest index of refraction probably that you'll run across. So that's really fast. They've gotten the speed of light down to, I think, around 30 miles an hour in a super cold, near the absolute zero osmium cloud or something. I don't remember.
Stop.
Bose-Einstein condensate made of osmium, I think it was. All right, which is really, really slow. You could drive a car faster than that. Okay, will you sketch which way the light ray goes in both cases? Water to air, plastic to diamond. Go. Yes. Okay, first thing to decide is, what are the indices of refraction? 2.42, and then this is going to be, 1.4-ish, something, right? Air, 1. Water, 1.33. Okay? Next thing you might want to do is to draw your normal. And then decide which way it's going to go.
Go closer to the normal.
Okay, this way. Will it turn
Down.
to the right or to the left?
To the left.
To the left. How do you know? Because it's going from slower to faster, it speeds up and turns away from the normal to get a bigger angle, right? Bigger speed, bigger angle. All right? Okay, practice marking your angles, please, because this is where students have problems. This is your theta 1. This is your theta 2. Theta 1 and theta 2. All right, what about this one? It's going to go closer to the normal. Okay, so it's going to be like this. This is theta 1 and this is theta 2. Okay, will you please mark your reflected ray? Because the light ray, when it hits the new medium, remember, some is reflected.
It's the same, right? It's the same.
Okay, where's your reflected ray?
Wait, which one? That one?
This one?
Yeah.
Which way does the reflected ray go?
This show was the original, right?
Same, right?
This way.
Oh, good question. Which one was the original?
The bottom one.
Bottom one?
That one, right?
Yeah.
Okay.
Okay, which quadrant will the reflected ray go into? 1, 2, 3, or 4?
1, 3.
1, 2, 3, right? And it's going to reflect this way with theta 1, right? Okay, so quadrant 2 gets nothing.
Nothing.
All right, over here. Which quadrant? 1, 2, 3, or 4? Fourth quadrant. Where this is theta 1 again. So your reflected and your refracted ray. Right? Okay. Let's do another one.
That fell.
Yeah. Okay. You have a glass prism. Looks like a pyramid. A glass prism where the light ray comes up and hits the glass prism coming from air. Okay, sketch the light ray till it exits the prism. Sketch. Make it big enough. So I'd like for you to sketch both the reflected and the refracted ray. Make sure you draw your normal lines at each surface. Now, drawing your normal lines sometimes is challenging for students. There's a way to always get it right. Just take a sheet of paper. Set it right there. And there's your normal line. Right? Okay, so this right here would be theta 1. Okay, where to from here? Instead of going straight,
There's so many of them.
it's going to go toward the normal. Very good. So it's going to look something like that. Now yours may be a little higher or a little lower. It doesn't really matter. What's important is that your theta 2
Smaller.
is smaller than theta 1. Okay, now what about your reflected ray?
If you put like another line there.
Yes, okay. Let's do your reflected one first. So there's your reflected one, where that's also theta 1. Okay? I think I drew mine a little too small, but that one should be the same as that one. Okay, now here's where it gets ugly. I have a new normal line, right?
Yeah.
My new normal line is perpendicular over here. And so now I need a new angle. Now here's where the math gets ugly. So let's go through the math. I'm going to make up an angle. Let's say that this is a 60, 60, 60. Would that be right? Equilateral triangle. You okay with that? Let's say that this angle right here turns out to be, what do you want to make that? 40 degrees. Okay? I'm just making an angle up. Because I want you to do the math. Because it's in your e-homework. Okay, what's the angle over here? Because this angle right here is my angle of incidence.
Are you halfway that on the?
Oh,
Um,
it doesn't matter. Okay, I'm going to enlarge this so it's a little easier to see.
what the angle? That angle. They're equal.
Okay, everybody. Up here, this is 60. Right? I made this 40. Okay, if that's 40, what's this angle?
No, it's got to be 140.
50.
It's
Oh,
50.
Oh, yeah.
It's 50 because it's a right angle. If that's 50 and that's 60, what's that?
70.
That's 70. How do you know that?
Because it's, yeah.
Because these three must add up to 180. Okay, if that's 70 and that's 90, so what's this?
20.
20 degrees. See how to work your way around? So you work your way around with right angles and triangle rules. Right angles add up to 90, triangles add up to 180. Okay? You work your way around. Okay, now we're not quite finished. Where does the light ray go when it exits?
It goes,
Does it go up or down? It speeds up, so therefore it goes down. Did you catch that? Because if this is theta 3, this is theta 4, and theta 4 must be greater than theta 3. Where's my reflected angle right here?
It's gonna be.
Because here's my first
20
reflection,
degrees, yeah,
and
20
here's my
degrees.
refraction.
20 degrees.
Ah, this one hits here. Some of it passes through, but some of it reflects that way, right?
And then it never
when
ends.
did it reflect?
Yeah, now technically it's going to keep going around and around and around.
And so
Now
it's
that,
perpendicular.
well, unless it hits perpendicular and it'll go straight out, but then some of it will bounce straight back too.
And then it'll go back where it came from.
It'll go back where it came from.
Oh,
Oh, no. Okay, here's the deal though. Why will we stop worrying about these after a while?
Because they're so it's so weak.
Yeah, because this is 100% of the wave, and if this is 50%, and that's 50%,
That's 20.
that's 25%, and that's 25%. You see that eventually it gets so dim you can't see it, right? All right.
That's crazy.
All right, so we're going to have to brush up on our geometry, right?
What? Geometry?
Geometry.
It rings a bell, but, you know.
And you say, but wait a minute, geometry, I'm not worried about geometry because there's no angles in the problems. Why, yes, there are.
There's 1,000 angles.
Okay, here you go. Snell's law. Snell's law describes the exact angles, how the angle of incidence and refraction are related. Snell's law is for waves that transmit, not the waves that reflect. The part of the wave, that reflects is covered by the law of reflection, so the angles are the same. Snell's law covers only the refracted part, the part that transmits through. The transmitted part goes by this. It's really simple. You've worked this last year.
Yeah, we did.
Okay, so let's go from water to 1.7 glass. Let's have it come in like this at an angle of 40 degrees. All right, what's the new angle inside? The reflected angle's easy, right? The reflected angle's at 40.
Fastest now, so towards the north.
So it's going to be closer to the normal, right? Because it's going to slow down.
So we expect a good angle.
So we expect an angle less than 40. So all we do is just plug in. I'm coming from water at an angle of 40 degrees. I'm going to glass, 1.7, at an angle of, I don't know. And I shall find out. Okay, everybody calculate that quick. Let's make sure you know how to use your calculator.
30. I got 30.1 and
Oh,
30.2.
okay, about 30 degrees, right? Excellent. You did not get that?
I didn't get that either.
All right, if you didn't get it, you need to check it. All right, so let's say you're playing around with your laser near the lake. Okay, you got your laser out here, and you're shining your laser beam from air at the water. Okay? Is there any way that you can shine your laser beam and it not go into the water? How?
You're allowed with the water?
Point it at the water.
Okay, you could not point it at the water. You could go like this, haha, it didn't go into the water. Or point it up. But is there any way for you to strike the water with your laser and it not, at least some of it, enter the water?
Probably not.
Yeah.
Well, eventually there will be a threshold.
Because if you shoot it straight down,
Wouldn't it?
it's going to go straight through. If you shoot it off at an angle, it's going to bend toward the normal, right? If you shoot it out here, it's still going to bend toward the normal, right? If you even shoot it way out here at an angle like that,
It'll still bend.
it'll still bend toward the normal and enter the water, right? Now what happens is that the shallower the angle, the more reflection you'll get, but at least some of it will enter the water, right? Every time. Okay, now, not to be outdone, your evil twin
Below the water.
steals your laser and takes your laser below the water
And drowns.
and shines your laser beam straight up.
Yes, he drove.
And what happens to that laser beam?
Go straight up.
Okay, some of it reflects, but a lot of it goes through, right? Okay, and then they shine the laser this way. And then what happens?
Some reflect, some bend.
Some reflects,
Away from it.
A little bit.
and some of it goes through. But instead of going straight, which way does it turn?
Towards the
Right.
surface.
Towards the surface or to the right, away from the normal. Okay, now they shine it out here. And then some of it reflects, and some of it bends towards the normal. Does anybody see the problem we're going to have?
It's gonna go.
Bends towards the normal. You just.
Yeah. Sorry. It bends away from the normal. Thank you.
You're gonna
I
have.
don't know. Way on the surface.
Yes. Does everybody see that? Theta 1, theta 2. Theta 2 is getting so
to
big that it's eventually going to come out here, and theta 2 is going to be right on the surface.
And the entire ocean will be lit up with green light.
Now you still get reflection. This theta 1 here equals, or what we call the critical angle. Okay, when you're at this angle, the critical angle, your refracted angle equals 90. So at theta critical, when theta 1 equals theta 2 equals 90 degrees. Okay? All right, here's the deal. What if you go beyond the critical angle? Out here.
They'll just all reflect.
Yeah, so what happens is there's no place for the light ray to bend anymore. Does everybody see that? It's bent away, 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 nothing left. When theta 1 is greater than the critical angle, all of the light ray reflects. And you get total internal reflection. All right? Now, some of you have experienced this. Next time you go here, go swimming tonight.
Hey.
All right?
Homework assignment.
Homework assignment. Go to the local pool. Jump into the pool. Lay on the bottom of the pool and look straight up.
Oh yeah.
How am I going to lay on the bottom of the
Let the little drink.
Carry weights. Here, we'll tie some concrete galoshes to you.
Tie me by my hair.
I guess you're just really dense.
Wear a lead overcoat. All right, and when you lay on the bottom, quiet. When you lay on the bottom and you look straight up, you can see out. But as you start to look at an angle at the water, eventually you'll reach a spot where,
You see the edge, and then nothing.
yeah, it's not that you won't see anything. It looks like it looks dark. The water somehow, the surface of the water turns dark. You know why it looks dark? It's because it's becoming a mirror. And what you're seeing is the bottom of the pool.
So if we look at the bottom of the pool,
If the pool is big enough,
You're seeing the bottom of the pool.
so
In
you think
fact,
you're like leaving the pool, but you
Here.
just hit the bottom.
do this. Have your friend stand like this in the water while you lay on the bottom of the pool
What the hell? No.
and you look this way at them.
I know he's not thinking.
Okay? And here's what you'll see. You won't see this person. You'll see this.
oh,
And why do you see that?
because it's
Because
above.
you're seeing the reflection of the bottom of their body because you're beyond the critical angle.
But wouldn't you also see a reflected? If you're not
You
above
see the bottom of them in the water,
And
and
then
you
their
see
face is
the
going to be on the
reflected part.
bottom of the pool.
Just a floating head. You have to get them to stand on their head and
I can see you all now. You're going to go home tonight. You're going to go take a bath, jump in the bathtub.
that does not.
It's not working. He lied to me.
Not working.
I don't
Try to
think
do
you
one
wouldn't
thing.
be able to get a critical angle with the one for the bathtub.
Okay, here. Here's one you can do in the bathtub. You ready? Okay.
Yeah, it cleans your body.
That's right. Here's your experiment.
Hey.
All right. And then here's your foot.
Because we're missing one.
So it's a cartoon foot. All right. Now, if you look with your eyeball this way,
What is wrong with their eye?
It's a, yeah.
with your eyeballs this way, which way does the light ray bend?
It's towards the normal.
Toward the normal. So what you see in reverse is the light ray goes this way and then this way into your eye.
So you blind yourself.
No.
Put your toe. The laser.
So you see your foot in a different spot. Now, what I want you to do
Like when pencils put them in.
is I want you to lift your foot out of the water, have your foot up here,
You see it twice.
okay? And then I want you to lower your foot into the water. And when you lower your foot into the water, yeah, it's going to get shorter as you lower it into the water. It'll get, in fact, whatever the length of your foot is, divide by 1.33, which is the index of refraction, it'll get that much shorter. That'll be the new length of your foot. You ever notice people standing in water, up to their waist in water, and you look at the lower part of their body, the lower part of their body looks stubby?
They're like midgets.
Yeah. Because the light ray bends, and it compresses them.
What is it when you put a pencil in a glass of water and then it looks broken?
Yeah, it looks broken because the light's bending as you look into the water, so it's an optical illusion.
So length equals.
All right.